Okay, in this video, I'm going to cover an exercise where we are comparing Poisson and negative binomial regression. This is involving data from the 2014 college football season. And what we're basically doing is predicting the account outcome, specifically the number of wins associated with a team during that season. So we have essentially fair number of teams here, about 128 teams, although we don't necessarily have data on all of them, and we're predicting the number of wins associated with those teams. It is important to note that the number of games that the teams play can vary to a certain extent, although most of the regular season games, or the number of regular season games, add up to about 12. You do have circumstances where weather or some other factor during the season may prevent or essentially create a cancellation. And then also teams vary in the number of games because of some teams play in conference championship games and also bowl games. So you also have that factor impacting the potential number of wins that's observed in a data set. So what we're going to do is we're going to create an offset variable to account for differential rates of exposure. And just really quickly, this is just at the IBM support site where they are actually describing offset variables. And so they're just kind of noting that each case may have different levels of exposure to an event of interest, such as in this case the different levels of exposure would be the games. And so in each game that's played, you have the possibility of winning or losing, and then that would have an impact on the count at the end of the year. So we're going to create an offset variable to account for differential rates of exposure for the teams. So at any rate, like I said, we're going to be comparing Poisson regression versus negative binomial regression as well. So our variables in the data set include football power index scores. This is basically obtained from the ESPN website. And so this is just basically preseason power index ratings. And then also we're going to use a number of true home games each team has played during the season. So there is variability in terms of the number of true home games teams play. So we're going to see if that has an impact on the number of wins observed as well. So to start off with, what we need to do is to create our offset variable. So we have our variable right here, number of games, and that's just basically taking the number of wins and adding it to the number of losses. We don't really have any, there are no more tie games anymore. So you can just sum up these two columns right here and that'll give you the number of games. So we're going to create the offset variable by going to transform compute variable. And this is what I was already kind of working with, but I'll show you again. Basically, we'll just create a new variable. We'll just call it log number games. And the target variable is up to you how you want to name it. I'm just being pretty descriptive here. The numeric expression we'll type in ln, and then inside the parentheses we'll just put the number of games variable and in parentheses. And so when we click on OK, we end up with the new variable right here. So this the natural log for the number of games. And so that's going to be our offset variable in our analyses. So next, to run the Poisson regression, we'll go to Analyze, go to Generalized Linear Models, click on that, and then we're just going to click on Poisson log linear. Response will be the number of wins. Predictors will include FPI and the number of home games. So that's the num-HS right here. So then we're going to move our offset variable over to this box here. Go to Model, and we're going to move both of these variables over to the Model box. Under Statistics, we'll also ask for exponential parameter estimates. So we'll click on OK, and so you can see that we get just a description of our model. So it's a Poisson regression, link functions, log link, and then our offset variable here, our information about our predictor variables and so forth, and then various goodness of fit measures. We're going to scroll down and look at the omnibus test. And so this test right here, this is a likelihood ratio chi-square test. It's testing the fit of our model containing the predictors against a null model with no predictors. So if this is statistically significant, that would be an indicator that we have a significant improvement in fit over a null model with no predictors. So that would be the case right here. When we look at the parameter estimates, you can see we have the unstandardized regression coefficient. And basically, we would interpret these values as the predicted change in the log count for the number of wins for every 1 unit increment on the predictor variable. So you can see right here for FPI, the predicted log count for the number of wins per unit increment on FPI is 0.021, so it's increasing. So essentially, a positive value on this is indicating that higher levels of preseason FPI are associated with a higher predicted count for the number of wins. Number of home games, or basically you can see right here that we have a negative value. So basically, higher number of home games would be associated with lower expected count. Now, it is important to note that, and that's a negative coefficient that's reflected right here. It is important to note that the FPI was statistically significant in the model, whereas the number of home games was not. So that's not significant. So just kind of looking at a bit of a write-up, if you will, where you can see that I would write this up to say the model containing the predictors, the full set of predictors, represented a statistically significant improvement in fit over a null, no predictors model. You can see right here we have the chi-square value and everything that's presented in this table. Looking at our output in terms of the parameter estimates, you can see that preseason FPI was a significant positive predictor of the number of wins. Remember that this is not, the coefficients are not reflecting changes in the number of wins, but rather the log count or the log number of wins. So it is important to note that although a positive coefficient would reflect predicted increase in the number of wins, the actual coefficient is referring to changes in the predicted log number of wins or log count of wins. So that is important to note right there. So at any rate, we see that preseason FPI, we had a positive coefficient. It's reflecting that preseason FPI is positively predicting the number of wins. So more specifically, if we want to be more descriptive about what the coefficient means, we could say for every 1 unit increase on FPI, the predicted log count of wins increased by 0.021. Over here, we have the incidence rate ratio. So we can basically say that that for every 1 unit increase on FPI, the incidence rate increased by a factor of 1.022, and that's this value right here. If we want to talk about percentage change in the incidence rate, then we can just simply take the number, the incidence rate, subtract 1 from it, multiply by 100%. We can see that we could say that for every 1 unit increase on FPI, there was a predicted increase of 2.2% in terms of the incidence rate. So that's essentially how you can interpret that. All right, so that's oh yeah, and by the way, so looking at the number of true home games, that was not significantly related to the number of wins. Just kind of looking at the coefficient right here, we could say for every 1 additional home game included in the schedule, the predicted log count of the number of wins decreased by 0.04. So that's this right here. The incidence rate ratio indicated that for every 1 unit increase on this predictor, the incidence rate in terms of winning decreased by a factor of 0.961. So that's this number here. If we wanted to talk about the percentage of decrease in the incidence rate, we can compute that by taking subtracting 0.961 from 1, multiplying by 100%, and that would give you the percentage decrease for per unit increase in terms of the number of home games. So now let's look at the negative binomial regression and we're going to leave the dispersion parameter left at 1. So we're just going to go with the default on this. So to do this, we'll go to Analyze, Generalized Linear Models again. And in this case, under Type of Model, we'll click on Negative Binomial with Log Link. And leave everything else exactly where it was. So we'll click on OK. So now you can see that negative binomial is noted right here. We still have our offset variable included and so forth. When we scroll down, you can see that the omnibus test result, our p-value is 0.06. So if we were using an conventional alpha of 0.05, then this model would not represent a significant improvement in fit over the intercept only or null model. So right there you have evidence that the fit of this model is not so good. Now we can also look at comparison. If we want to compare the Poisson and the negative binomial models, we can compare these two models in terms of the AIC and BICs. And basically the preferred model is the one with the lower AIC or BIC. So using the AIC for this model, it's 663.241, whereas when we look at the AIC from the previous model, you can see it's 510. So the Poisson model actually appears to fit the data better than the negative binomial model. Then just kind of looking at the individual predictors, you can see that FPI was still a significant positive predictor, whereas number of home games was a negative predictor, but it was not statistically significant. So at any rate, just kind of going back, you can see again, just kind of comparing the negative binomial and Poisson models, you can see that again, that for the negative binomial model, this was the significance for the model. The Poisson model, this was the significance. So you can see right there that the negative binomial is not fitting the data, whereas the Poisson model would be considered as fitting the data. Then when we look at the AIC and BIC for the negative binomial model, this is model 2 versus the Poisson model, which is model 1, you can see that the AIC and BICs were lower relative to the negative binomial. So the favored model is going to be the Poisson model. And then, just kind of looking at the, again, at the individual parameter estimates from the negative binomial model, really there's not a whole lot of change in what these are reflecting relative to the Poisson model, but as you can see, FPI was a significant positive predictor of the expected count for the number of wins. That was significant, whereas the number of home games was not a significant predictor within the model.